Ja, nochmal guten Morgen allen der neu dazugekommenen. Wir fahren dann weiter fort in unserem Programm mit der dritten Präsentation. Ich darf Ihnen vorstellen, Dr. Maren Kasischke vom Fraunhofer-Institut IMS in Duisburg. Dr. Kasischke offered to me she can hold the presentation in English as well as in German. So the question is, I don't know how many international guests we have in the audience. One, two, three. So
three.
You would certainly prefer an English presentation, yes. I think most, if not all, German listeners can also follow the English presentation, should be no problem, especially if you can read the words on the screen. So I would say, let's go on with English, and we have enough time at the end, I guess, if there are questions to make everything clear. So the topic is harnessing edge AI for advanced failure prediction and condition monitoring. AI, the buzzword of the time, so we are very curious to hear your presentation.
Thank you. Thank you. So good morning to you all. I want you to think back to the last time that you went to the beach and got some of the beautiful Muscheln. Now I forgot, of course, a word in English, but you know, or stones also that you got from the beach, right? Maybe it's a couple of years ago, but you surely remember how you did it. Either you got the most beautiful ones that you wanted to have at home, or you got a bucket full of sand and then went home and looked for the most beautiful ones, right? So probably you did the first thing. You didn't take a whole bucket of sand home to then get the most precious memories out of the sand. So if you think about this picture, this is going to help you why Edge AI is an advantage when working with AI models also in industrial use cases. And this is what I'm going to talk today about, Edge AI, and also the next developments regarding Edge AI. So as the first example that I bring with you is still not my industrial use case, but it is for you to understand also the hardware development behind it. So if you think about the electrical toothbrush, for example, you had a motor and a battery, and that's it. Then the next generation, they thought, oh, okay, I can add a pressure sensor, for example, and then the light goes red if you have too high pressure. And I can also add Bluetooth. And with your cell phone, you can get the data about how you're brushing your teeth. But then the last generation, and I don't want to know how much it costs, but you can, with your toothbrush, in line have a position recognition and a 3D tracking of your cleaning movements. And this is all on the device, so you don't need a cell phone and a Bluetooth. Probably you can still do it, but it's still everything on the device, okay? So this is, I think, a very good and simple example of Edge AI. And what is next? Maybe not for the toothbrush, but for us today, on-device training, right? Because if you have an AI that you have trained for some kind of example, some kind of domain or use case, the probability that something is going to change afterwards is very high. So you need domain adaptations too. And what is the advantage of this domain adaptation and on-device training? Here I have in the first variant a standard way of a workflow when you're training AI models and then doing the inference, which means that you're playing the AI model on the device. So you get the data acquisition from some kind of sensor or from your industrial PC. You transmit the data either to the PC or to the cloud. do your training, and then the model needs to be quantized and compressed again in order to be then transmitted and made the inference at the model in the last step. So the idea of doing on-device training also is that you miss out all the steps between 2 and 5, and you do the model training on the device. And I don't want to paint a wrong picture here. You have to think that this model training that you're doing on device is more like an adaptation, right? So it's not, at the moment, not yet, that you can train the whole model with the first data that you get on device. This is still something that you need to do on the PC or on the cloud. But if you have some small adaptations or domain adaptations, this is something you can do on the device. So now I think we can say what are the advantages of edge AI. One is you reduce the data volume. This was what I tried to explain with the bucket of sand and the stones that you get from the beach, right? So you only transfer the data that you're interested in. Then you have also faster decision making and a better response time, because you're faster. You don't have to go to the cloud or to your PC. You're very near from where the data is being acquired. And of course, you have energy efficiency. So you think about carrying a bucket around full of sand or only with a couple of stones. And the last point, when you are able to train on device, you also have adaptability. And this adaptability, for you to get a picture, we have an example here. So if you look at a picture, you can think about, okay, the model maybe is being trained on a sunny day. People are wearing very clothes that is like for the beach, and it's hot. You have the sun, a lot of light, it's bright, and so on. And you do the training, you have a single domain, but of course, you will have winter sometime. And here you will have another clothes, other lighting, other temperatures, and you need to adapt your AI model to multiple domains. So the idea is, or the challenge, let's say here, is that you need to have an expandable AI model that with a few new training sets is retrained. And the anomaly detection, for example, that you're doing can be adapted to multiple domains. And getting a little closer to the industrial use cases, for example, here you can have a frequency-based feature extraction if you're getting data from a microphone or a vibration sensor, for example, and training an AI model. And the sensor system then is going to tell you, okay, this is an anomaly, or no, this is the normal case that is no problem. And then what is usually done at the moment is the system is telling you, okay, there's an anomaly, we have some kind of failure, and it is being transmitted to some place. But what if you get a human in the loop idea, that there is a human or some kind of system telling you what domain you have? So is this a real defect, or is this an anomaly that has been detected that is not a problem? It is maybe change of weather, change of lightning, some kind of domain adaptation that you need to do. So with some training points, not a whole data set, you can retrain your model. And this is the idea about on-device training. So the advantages, of course, is that you have the new domains for the anomaly detection, and you have adaptability of condition monitoring for different operational conditions. And now getting to the two industrial use cases. The first I brought is about machining. The idea here is that we predict the remaining useful lifetime of tools. So we have a retrofit vibration sensor that we have added to the holder of the tool. And even though the tool wear is happening here, we're able, with gathering data, of course, and training the AI models, to predict how long is this tool going to last. And this is very useful because at the time it is done by operators who are listening that the tool is not working well, or that they take it out and do a test with the fingers. So, and the good thing about this sensor system, it's a retrofit sensor system. But here also Edge AI comes into place because we have a lot of data, vibrational data that is being gathered, and we don't want to transfer it all to the PC or the cloud and then do the inference, but to do it directly on the sensor system. And what is the possible advantages for machining? One is that if you have this kind of security while machining, and you know how long my tool is going to last, you can be a little more, let's say, faster while machining. This means people are very careful because they don't want the tool to break. But if they have this condition monitoring system that is also telling you how long it's going to last, you can increase your machining speed. And then you have a higher productivity. And the example we have here is the set of training data. You see it here. We trained with 7 tools, had 10 measurements per tool, and had a 5-minute training for this data set. And this set that you see here with another speed wasn't trained in the model. And even though the AI model didn't know this kind of speed, it was able to predict with an accuracy of 8 minutes when the working with this tool was 65 minutes, that it is going to be breaking, or the wear is going to be too high, so that the quality of your tooling piece that you want to produce is not good enough. So this is like the first use case, the first example that I brought to you. We are in the development of the adaptability, of course, that, for example, okay, we say, in 8 minutes you need to change it, but the operator can tell you, okay, no, this is still something, a tool that you can still work with for an hour, or it's still okay or something. So this human in the loop is something that we're working at the moment. And what we use for this is we call it Predictive Box, is a development platform. So don't be scared about how big it is. It's on purpose. We did a over-instrumentalization. This means that we have a lot of capability with this in order to, in the next step, be able to say, okay, we don't need this kind of computing power or this kind of sensor. We maybe can use another sensor. But with this one, we were able to produce the data that I just showed, and we have different interfaces, like, for example, Ethernet, or it can be also adapted to a Profibus and so on. So in order to also connect it to the industrial PCs of the machining machines. Yeah. So changing to the next use case, we're going a little more into the power electronics. This is a project that we are also presenting at the fair that is just on the other side of this place. It is the PCIM fair, because here we were also doing the condition monitoring of the transistors. So what is the idea here? We want to integrate into this power module an intelligent motor control that is doing the condition monitoring of novel transistors and of the load, which in this case is a motor there. And here, what we are doing is that we don't want to have additional sensors. So we want to work with the sensors that you already have within the electronics of your power module. Here, for this, you see Power Care. It's a big project that we're doing together with colleagues from IISB and ISIT. They are also at the fair. And the idea here is to use embedded AI in order to do the failure prediction, so going to predictive maintenance compared to reactive, planned, or proactive maintenance, which is something that is usually done at industry. And the second idea is also to use novel gallium nitride transistors. So usually what you have are silicon carbide transistors, and in this case, the colleagues from ISIT are using novel ones. So why are we getting together with 3 institutes to do this? It is because ISIT is developing the novel transistors. IMS, we are getting the AI into the motor control. So as I explained at the beginning, right? It's the difference if you're doing the inference on the cloud or on the PC or on a microcontroller or an FPGA where you have hardware, not such high computing power. And the IISB has a lot of motor stands where they get all the data about when they have a failure, so they were able to develop an AI to predict the failure of these motors. And what we're doing is to get into this inverter a controller that is based on RISC-V, which is a open source a processor instruction set. Compared, for example, to ARM, that is not open source, we're working with RISC-V that has, we have developed it so that it has AI accelerators. This means that it is an instruction set that can be used to do the inference of AI models in order to do the failure prediction. And the idea is to get it really everything into the inverter. And as an example, I'm focusing today on the electric motor, just for you to have an idea what is going on with the data and what is the result, let's say. We want to have in the graphical user interface, and we've already shown this too, that we can say there is a problem with the motor status. On the first kind of problem can be the bearing fault, demagnetization, or other. So we were talking about anomaly detection, and if you know which kind of anomaly it is, you can say it is bearing fault or demagnetization. And what the colleagues are doing here is to gather the data, which is the phase current that they get from the inverter, from the 3 phases. Then they do a fast Fourier transformation and a principal component analysis. So up until here, you don't have any AI, right? So this is standard signal analysis. And in the last one, they do the anomaly detection to really see, okay, this data that is in some kind of axis of our component analysis is an anomaly or it is not an anomaly. And then they get the result, okay, there is a bearing, it's working, or there is a bearing fault in the motor. And what we were doing is that we had this huge AI model with a very high size, let's say, so like 7 MB or 76 MB. And with our framework that we have, which is called IFAS, AI for Embedded Systems, we optimized the quantization of the model, and we're able to reduce it by down to 320 kilobyte RAM and 320 kilobyte flash. So the idea here, as we saw at the beginning, if you have the AI model that it's smaller, you can do the inference on the edge. And of course, it would be great if you have some kind of domain adaptation to do the last retrainings here on the device itself and not going back to this huge AI model that you need to quantize and compress then afterwards again, right? And with our with our framework, IFAS, we're able to do this on-device retraining. Yeah, and with this, I am closing my talk. I hope you got some idea of the advantages of Edge AI and what are the next steps that we're doing the on-device training, and about the two use cases, machining, where we're doing the prediction of remaining useful lifetime, and in the power electronics, the on-device monitoring of the motors as a load and of the transistors. And I would like to invite you to visit us here at Sensor and Test in the booth 1. It's just on the corner of the hall 1606. And of course, if you have the chance to go to PCIM, our colleagues are there at the hall 6 and the booth number 260. And now I'm open for any questions you might have. Thank you.
Well, thank you, Dr. Kasischke. Yes, we have a lot of time left, and so there's possibility to put your questions here and immediately. Of course, then afterwards, you can go to the booth and discuss problems there or discuss your questions there.
Of course, also in German, if you like to make any questions here.
Yeah. Wait, I come with the micro.
Thank you very much. My name is Thomas Kuttner from University of Federal Arms in Munich. And my question is, which method do you use for bearing detection? Is it simply in the time domain by RMS or crest factor? Or is it based on the basic fast Fourier transformation? Or do you use also more advanced techniques like envelope detection with the Hilbert transformation or things like that?
Yeah. So, of course, these are the work from our colleagues from ISV, but it is definitely a time domain data that we get from the 3 phases of the current, and we do the FFT and then the Hauptkomponentenanalyse, I always say it there. So this analysis. But of course, yeah, the colleagues from ISV, if you want to go really deep into it, they're at the booth at PCIM, yeah. Of course. Okay.
Any more questions? No, not for the moment. So again, feel free to visit Dr. Kasischke at the booth, and she will surely be happy to show you around and discuss further problems and further questions with you. Yeah. Well, thank you. It was very interesting, and so we have some minutes of spare time, but don't go too far away. Then half of the hour we will continue with our presentation. Thank you.